Thank you for joining us. This is our last session of this year's online seminar. Uh, as I mentioned, we have a very packed program, so I'm not taking much time. Today, the session will be shared by my dear friend and colleague, Luis Felipe Lopez, General Manager of the Base Baha'i Foundation. And we start with very exciting news about a new book. So, Luis Felipe, please go ahead.
Thank you, Edwin. And first of all, thank you to INBAR for inviting me to be the moderator of this session. It's always a pleasure, and I really enjoying to share with the bamboo community all the advances in research and in the technology. So, as Edwin was saying at the beginning of this session, like we have in the, I think, one or two sessions before when we launched the manual for construction of single story houses. Today we're going to do also the launching of a new book. These are great news for all the bamboo community around the world because during the last, I would say, 4 years or 5 years, a group of very, very good professionals were working in the development of this book. So I want to invite David Trujillo, the main author of this book, to make us a short presentation about the content of the manual, who was involved, and then at the end, we will have a short conversation between David, myself, and I hope the other two authors can join today. They are in a different time zone. We hope they can make it. If no, it will be only David and I. So, hello, David. Good evening from Manila.
Hi, Luis. Hi. Good afternoon. In here in the UK. Is it okay that I share my screen?
Yes, go ahead.
Can you see my screen?
Yes, not yet in presentation mode, but yeah,
I'm in
perfect.
presentation mode now. Yep.
Yeah.
Okay. Yes. Thank you very much for that introduction. And yes, today's sort of the official launch day. I think the real day that this is going to become fully available is the 2nd of December. So we are launching the manual for design of bamboo structures to ISO 22156 version 2021. It's a real milestone because we've put in a lot of work in writing this manual, but also because I don't think there is anything halfway similar to this in the field of structural engineering. The book was published by the Institution of Structural Engineers, and thanks to the sponsors of Base Baha'i and INBAR, the book will be freely downloadable, which is uncommon for their manuals. So the idea is that this way we can ensure that it has as much impact as possible. Here is the group of authors. So it's myself, Professor Kent Harries, Sebastian Kaminsky, and Luis Felipe Lopez. I'd also like to take the opportunity to acknowledge quite a lot of people that helped us, from the Journalyn from Base Baha'i. She helped us with a lot of illustrations. Lee Baldwin and Jenny from publishing, and then an extensive team of reviewers that helped us out with ensuring that this book was as good as possible. The book has 10 chapters. The first one is an introduction. The second one talks about the bamboo supply chain. The third one about grading and mechanical characterization of bamboo. The fourth one is principles of structural bamboo design. The fifth is durability. Sixth is design of full column bamboo members. And seventh is design of bamboo connections. 8 is composite bamboo shear walls. 9 is research and development gaps and needs. And 10 is worked examples. So when we compile this book, we try to take an engineer from the journey of thinking about where they're going to get their bamboo, which seems trivial, but it's really important to think where you're going to get it from, all through determining the mechanical properties, because you might not have this information to hand, through thinking how you design it, how you ensure that it's durable, how the elements are designed, how the connections are designed, and a typology of construction called composite bamboo shear walls, which I'll talk a bit more about later on. And also for the academics, for example, in the room, pointing to things that we need to know more about. And finally, something that's of course essential is to point out to people how you go about designing things. The book contains detailed explanations. We try to make things very clear. So we've used things with like tables and flowcharts and graphs to make concepts as clear as possible. We also explain the theory behind some of the things that are contained, not just in the manual, but in ISO 22156, because the authors were also part of the team of people who put together ISO 22156. So we know what was behind the thinking, and that's the advantage of the manual. It explains the how and the why. It contains useful guidance, and so in this instance, about how to ensure that your buildings are durable. It's one of the things I will hopefully discuss later on, is because this manual is not just a... Whoa, what happened there?
We can hear you, David. It's okay.
Can
And
you
we're
see my presentation? Yeah. It's probably the first document that contains such detailed information about durability of bamboo, how to ensure durability. It's also probably the first that contains so much information about how designing composite bamboo shear walls, or bareque and cemental for Latin Americans in the room. And it's got lots of illustrations that explain things, how they work, and a lot of text that clarifies things. And of course, the other thing that it contains, which we hope is going to be helpful, is worked examples, which take people through how you use both the manual and the standard. So that's sort of the basics of what the manual now introduces. Oh, my camera's gone funny.
Yeah, I think you are blurred now.
I'm blurred. I don't know. It didn't like me any longer. So I don't know. I would like to start by saying that the book, though it's aimed at structural engineers, and it's to a certain extent the first in its kind that's aimed at structural engineers, it's also useful to architects and other professionals for other reasons. For example, it's useful to architects in chapter 4, which outlines the concept of how you design, with how to ensure design is appropriate to bamboo. And chapter 5, that talks about durability, it's also very much in the realms of the architects. But it also talks to other building professionals about what we engineers are after. So though it's, I say, aimed at structural engineers, it helps many people. And because it's freely downloadable, it won't be any difficulty to get hold of, and you take a look at it. And as I also mentioned, I think it's also one of the first books that covers some topics in as much detail, even if they're not just about structural engineering, like durability. Luis, do you want to add something?
Yeah, so but first, thank you, David, for this good presentation about the content. And I'm so happy and proud to be part of this. And also from Base Baha'i point of view, we are really, really happy to sponsor and to make this together with INBAR. Of course, we put our efforts together and our resources to make this book available for everyone out there. And I think that's what makes this book special, no? Because bamboo is present in countries that sometimes don't have too many resources, and people in those countries probably will not have money to pay a lot of cost for a book like this, and make it the book free of access for everyone. I think it's a big achievement. Just to mention that the content is incredible good. So I want to ask you, David, do you think this book could be a game changer in the bamboo engineering world?
Oh, well, I certainly hope so. I mean, this is why we've invested all this time in doing this. I mean, we've spent so long producing this book, and we hope it to be a game changer, because for the first thing is that there was nothing like it. There was nothing out there similar to guide engineers on how to design safely with bamboo. Obviously, ISO 22156 came out in 2021, but codes and standards are hard to sometimes interpret, and that one is particularly hard to follow and understand. So this is, we hope, a game changer. I should take the opportunity. I've seen something in the chat. This book is only for bamboo columns, so stems, poles, not for engineered bamboo. Yeah, certainly hope it's going to be a game changer.
So I can see now that Kent joined us. I'm so happy that you make it, Kent. So welcome to the forum, and I'm so glad that you can do it because you were very, very important in the development of this document. So welcome to the conversation, and please let us know how was your experience. Why a professor from Canada that works in the US get involved in this Utopia project?
Oh, we don't have time for that. I just really, again, reiterate what David said, what you said, Luis. This was a great project to work on. I think it's an absolutely critical project going forward. And we've already been discussing, how we now improve on 22156. And dare I say, work on the second edition of this document after that. And David is going to leave the room now. I can see that. I encourage everybody to get a copy of this. I guess it will be out on Monday, available Monday, I think, from various sources, INBAR, BASE, and of course iStruct-E, and dive right in.
Great. Kent, I think it was this morning or yesterday morning when we were talking about how this presentation is going to be. And then that nice feeling of finishing a project after 4 years disappeared when you mentioned that now we need to work in the new standard project, the new version from the new book. But that's how these things are. And then actually, I'm very happy to be part of this and to share with all of you during this time.
Well, I think it's a very important point, Louis, and I want to bring to everybody at this seminar and everybody who will be watching it later is codes and standards development is always a moving target. And particularly 22156 is a version 0 document. It really is the first of its kind. It is imperfect. It has gaps. We need this entire community to come together to improve upon it. And to a large extent, this book helps to kick that process off as well.
Absolutely. And I think the book is going to help us also to figure out where we need to put our efforts in research for the coming years. So I think I just want to say thank you again to INBAR, to David, to Kent. Unfortunately, Sebastian Kaminski was not able to join us today. This is a great achievement for the bamboo world, for all of us. And I think as some people is asking where the book can be downloaded, in December 2 is going to be available in the websites of the Institution of the Structural Engineers and INBAR website and in Base Baha'i website. So you can choose your preference and then download it from them.
Yeah, that's one of the questions that's out there. There is one other question that's in the chat that's emerged, which is fire protection. I don't want to go too much, but we do talk about fire in the manual because obviously we couldn't write the manual about bamboo without talking about that. But that's covered as well. We would like to maybe in the future produce a version in Spanish. That's a sort of a wish that we would like to do, but that's something to look into the future. And of course, as Kent has mentioned, we also aim to start working on revising ISO 22156, and we invite as many people as possible to join this effort.
Perfect. So again, thank you, Kent and David. It's a pleasure to have both of you today. And now we will move to the webinar. And I want to invite first the first speaker. In this case is Jonathan Alexander Duque from Universidad del Valle in Colombia. Our seminar today is called Towards Mainstream Bamboo Construction, Engineering with Bamboo from Laboratory Tests to Building Codes. So for the last, I will say 20 years, we have been working, all of us, in the development of building codes, equations, formulas, tables to design, trying to close the knowledge gaps that bamboo engineering has. I mean, 30 years ago, when Jules Janssen started, there was absolutely nothing about mechanical properties, design of structural elements. And these 25 years or 30 years of research in many countries and many people has helped the development. That's a good news, and the result of that research is the book that we just mentioned and the standards like the ISO 22256. However, still we need to work more. There is a lot of gaps that still in the topic of connections, for example, we're still not ready. And today in this session, we are going to show the work of very interesting researchers tackling some of those topics. So is Jonathan already online?
Yes.
Hello.
Hi, Luis Felipe.
Hi, Jonathan. Okay, I don't see you in the screen yet, so...
He's there.
Let me share my...
Hi, how we can put Jonathan in the screen, Edwin, because I'm seeing you.
I can see him. Jonathan, can you? Yeah, he's coming.
Okay. Okay, Jonathan. So okay, now I don't see Jonathan, but I see the presentation. So before Jonathan starts, Base Baha'i has a collaboration with Universidad del Valle from Colombia. We started the collaboration a couple of years ago, and part of that collaboration was the thesis of Jonathan, and he came actually to the Philippines a year ago. He stayed with us a couple of months working in his tests and his research, and today he's going to show us his results and the topics he's working. So, Jonathan, please can introduce yourself and then proceed with the presentation.
Thank you very much, Luis, for the introduction. I truly appreciate that you are here to listen this short talk. I'm actually I'm a doctoral student at Universidad del Valle here in Cali, Colombia, and I'm really happy now for this here in this seminar. So thank you very much for everyone. Okay, so my name is Jonathan Duque. Today I would like to show you a small part of my doctoral research. And that's it's mainly focused on the development of bamboo slats frames for shear walls. First, I would like to begin by saying that bamboo is a material for everyone. Thanks to its versatility, bamboo can be used in straight column form to build large and complex structure, and also bamboo can be bent to create roof system with a great architectural beauty. But this material can also be used to develop a relative simple structure that can represent a social solution for income communities. Another important application, especially for people in developing countries, is housing. For example, in Colombia, the housing deficit is close to 30%. So social housing projects using bamboo can improve the quality of life of many people, many families. So the evolution of Bareque construction into the cement bamboo frame technology system has led a structurally predictable and standardized construction method, which is now being used in projects with high social impact, for example, in the Philippines and the neighboring countries. Okay, these systems mainly use bamboo poles for the vertical studs in the walls or for roof structures, but these bamboo poles do not provide an optimal surface to execute some types of connection between elements. And for example, if you want to incorporate a flat wooden or fiber cement boards to complete the wall sandwich, so maybe it can be complicated with the pulse. In fact, for roof structure, it's often necessary to use small wooden blocks to level the surface before installing the tiles, the roof tiles. For wall construction, this challenge is addressed using crushed bamboo mats or esterilla and flexible metal mesh, which can adapt to the irregular surface, but this requires significant labor. All of this is due to bamboo's natural geometric irregularities, as bamboo poles can be conical, have varying diameters, or be quite oval shape, and all of which can complicate many kind of connections. And in addition, poles are prone to cracking, to volumetric changes that generate circumferential stresses and eventually longitudinal splits. All this factor often leads a high amount of material waste. So for this reason, we are proposing extracting slats by longitudinal cutting bamboo poles. This can be done manually or with simple machines, and then these slats are planed, taking care not to completely remove the outer surface, because we think this layer has the best mechanical properties. So with this processing, the inner curvature is fully removed, and on the outside we mainly remove the protrusions near to the natural nodes. This allows us to stack multiple slats together and create flatter surfaces that can facilitate the connections. So some advantages of this processing include more regular geometries, flatter connection surfaces, the possibility of assembling multi-slat members, and the development of connection with standardized dimensions. So with these configurations, we propose multi-slat members joined with 1/4 bolts. These are 1/4 inch bolts that can be tightened strongly, generating a high radial compression through the slats. And in some research have shown that this radial compression can increase the capacity of axle loads by 50%. By 50%. So in addition, this configuration allows thin steel plates, gusset plates to be installed, which we can connect multiple members in different directions, for example. So this can be a good idea. Another alternative to connect slats maybe is join natural or on plane slats, keeping their natural curvature. So the post here is try to reduce the labor. So this can be achieved using bamboo pins to form that we call pimbu elements, and with support from base Baha'i, we build a drilling and assembly table and a simple machine to produce pins. And using this equipment, we build both pimbu specimens and bolt connected specimens. And here, the bolts must be installed without preload to avoid this kind of cracking through the slats due to possible bending stresses. So we perform compression tests on these specimens to have a first characterization. So here in Colombia, we test 1 meter members built with the first constructive method, that is planed Wadwa slats with pre-stress or preload of the bolts. And in Philippines, we test 2.4 meter members built with the second construction method, that is on plain dendrocalamus asper slats, connect with bamboo pins, air, and with non-preloaded bolts. These are typical compression curves for first construction method, and we can see the load increase rapidly, reach a peak, and then the load drops due to the global buckling. And a similar response we observe for the second construction method. Here, the scales are different to better visualize the curve. We are analyzing the results through different approaches. One of these, we use a parameter that we call index ratio, which is the ratio between the effective moment of inertia to the geometric moment of inertia, where the effective inertia is obtained by rearranging or solving by Euler's equation and using the critical load, the experimental load that we found from the curves. In this graph, we see that the first construction method, that are these blue columns, achieve an index ratio greater than 0.8. So it's near to the optimal index ratio, that's 1. This represents a strong composite action of these elements. In contrast, the second method shows a more limited composite action. So these green columns represent some validation groups that we built with what was slats, but using the second constructive method to ensure that difference were not due to bamboo species. A second approach used some European equations to determine the imperfection factor that best fit the experimental result. Here, a factor of 0.39 provided a good fit for the first construction method. That is this orange curve. But for the second method, this approach was not valid because the results were too small, or yes, too small, we can say that. Okay, we also use finite element models to compare experimental and analytical results from the index ratio approach. And we found here good agreement with the numerical result, as can you see here. It's really near. So then we explore different joints configuration for slat members. We first propose the connection between 2 slats using a thin steel clamps and a couple of 1/4-inch bolts. And also we propose multi-slat connections using bamboo pins. But okay, first, in this proposal, we will try to do a kind of finger joint or finger configuration with these slats. So we complete the joint with bamboo pins, with wooden block, with a thin metal sheet and some screws. And we do a first characterization under monotonic loading of this kind of connection. For example, for the 2-slat connection, we obtain a maximum moment of 0.19 kilonewton meter and a rotational stiffness of 3.8 kilonewton meter rad, and ductility of 17.5. That was really high. For the multi-slat connection, the maximum moment in stiffness increased by 7 and 1.8 times respectively compared with the 2-slat connection, while the ductility decreased by about 7 times, because the holes near to the connection zone can generate stress concentration, become more brittle the joints, becoming more brittle the joints. We then propose a simpler and easier to assemble connection consisting of 2 multi-slat members joined with a finger configuration, as you can see here. And that is confined with 2 millimeter thick steel gusset plates, tightened with 5 16-inch bolts. And with this connection, The number of slats can vary freely in this direction, allowing for thicker members. We conduct here 10 monotonics and 10 cyclic tests using a reaction frame equipped with a hydraulic actuator in some sensors. Based on this monotonic experimental results, we developed a 3-linear analytical model that use the slat dimension and mechanical property to predict the monotonic behavior that are represented by these blue and green curves. We found here significant improvement in rotational stiffness, 2.3 times, and in ductility, 6.7 times higher compared with the multi-slat connection with bamboo pins. And using the beamline methodology that is usually used for moment connections, we could classify this joint as partially restrained. And the failure mode was consistent across the specimen. It was shear failures in radial longitudinal planes, as can you see here. Here's one of the cycle curve with 30 cycles. The red line shows the backbone curve from which these performance parameters were extracted. It's important to know that rotational stiffness and ductility in the cyclic test were about a half of those found in the monotonic test. This may be due to loss of friction and small relative movement that can be caused by load reversals. In several specimens, we obtain the complete or total fracture of the slats passing through the finger joint zone, mainly due to the longitudinal tension from the bending that are support for these slat members. Okay, so the goal of all this is to be able to build this kind of frames or skeleton using these multi-slat members in the vertical stud and horizontal joist. And that elements will be connected with moment resistant joints. So the connection I was showing now will be used at the frame corners. So we also need to develop the joints for intermediate nodes, and we plan to test different kind of bracing configurations and different clamping or coatings for this frame. So in this proposal, the frame thickness can vary depending on the number of the slats per member. We think the structural behavior could be highly predictable, and the system could rely less on cement mortar plasters to resist lateral loads, making it lighter. And in addition, there's a potential to incorporate wood, bamboo, or fiber cement boards, or to use conventional cement plaster. Okay, regarding the T-joints, we have made some progress. In the first phase, we propose several configurations. Here I'm presenting three. In the first proposal, the horizontal members are connected to the stud vertical member on both sides of the using one 8-inch bolts plates with 1/4-inch bolts. In the second proposal, the vertical stud rests on the top of the horizontal member, and that is confined by using a couple of gusset plates that are tightened with bolts. And for the third proposal, we use a gusset plate that is installed in the middle plane of the slats of both horizontal and vertical member. So in this case, the gusset is connected to horizontal member with bolts. So we have to do holes on the slats here, and is connected to the column elements by using a couple of clamps without drilling into the slats. Okay, in all this proposal, the column was fractured, failed. The column failed. So, which is an undesirable mode of failure. However, we could see that this third proposal performed best. So we conduct a second phase of experiments with geometric modification to this design. So we changed the aspect ratio of these plates. This distance was 116 millimeters, and it was reduced to 120 millimeters. And we test here three plate thicknesses: 0.8 millimeters, 1.5 millimeters, and 2 millimeters. Okay, for the thinner plates, failures occur in the connection steel elements, while the bamboo remain intact. For example, here at the 0.8 millimeters, the failure move was local buckling and shear tearing due to the bolt interaction here. At 1.5 millimeters, we observe only shear tearing due to the bolt interaction. And finally, for the 2 millimeter thickness, we observe a good failure. You can say that as the horizontal bamboo member failed, and some steel elements were plastically deformed, and I say that that was a good failure mode because was ductile failure, and so we estimate a ductility of 4.3. That is a good ductility, and based on these results, we select this connection for full monotonic and cyclic characterization, and it will be the next stage. Okay, so these are some preliminary conclusions, but before that, I would like to show you this first frame or skeleton that I'm finishing. And the idea with this specimens is to test under monotonic or cyclic protocols, first without bracing to test the work of the moment resistant joints that we are using here, and also we perform tests with different kind of bracing with steel platens or with bamboo slats, and when we try also with different claddings or coatings for these frames. So, okay, we found now the multi-slat member with free curvature and tighten bolts provide a high composite action showing index ratio higher than 0.8. The simplified corner connection shows rotational stiffness and ductility higher than the connection with bamboo pins, and the select T-joints show a desirable failure mode and good ductility of 4.3, and it will be fully characterized. And the wall frames will be tested under established protocols with different factors that I mentioned. So some acknowledgement for Jose Jaime Garcia, the tutor of this work. Luis Felipe Lopez is the advisor of this work, the Ministry of Science and Technology and Innovation of Colombia, and Base Baha'i Foundation for all the support. Thanks.
Great. Thank you very much for this wonderful presentation, and congratulations for the work that you are doing. I know the effort and the enthusiasm that you are putting to this research, and we really value all these achievements. So before we start the session of questions, I think we have a couple of questions already in the chat. I want to ask you, Jonathan, if you had checked the cost of the system compared like with traditional construction systems, or you are not yet in that phase?
Recording in progress.
Hi, Jonathan. Can you hear me?
Yes, I hear you.
No, I was asking Jonathan if did you check the cost of the system?
Can you repeat, please, Luis? I have some problem with the audio.
How it's going to cost the system if you think it's going to be competitive? Okay, so can you hear me, Jonathan? You are in mute.
I can hear you now, Luis.
Okay, so again, I repeat the question. So, do you know if the system is expensive, if it's cheap? Have you checked the cost of doing this?
Yes, I think this system is expensive, expensive in compare with the current system, because we have here more process, and we have we have the consumption of more energy here, but we think
because definitely, Jonathan, if you compare against round poles like normal bamboo, of course it's going to be more expensive because there is an industrial process. But what about if you compare the system with a different thing like laminated bamboo, like engineer laminated wood. Did you check that cost? I mean, the question is to know if you can make a competitive house in price. Do you think it's possible?
Yes, but I think it's possible because this technology is in a middle point, we can say, between the engineered bamboo products and the current bamboo frame, cement bamboo frame technology. So in compare with this high processing technology like engineered bamboo, yes, I think we can construct, build some good housing projects that can be competitive in some regions, but it's depend the region and the many factors, but that's possible.
Great. So, Jonathan, I think we have here a couple of questions in the chat. So I will start with the question of Tobia. This question said, did you compare the load that a traditional bamboo connection for round poles can resist versus your connections? There is any significant difference between those values? Have you checked that?
Yes. We have compared these results with several kind of joints, including joints with bamboo pulls or bamboo culms, and sometimes we found that these results are lower than some solid elements, but the solid elements usually have really have higher cross section. So sometimes it's complicated try to compare with some with the literature because we here have small cross sections, but if we check the efficiency to transmit loads or moments, we are finding that we have a best or a high values that are reported in the literature.
Okay, great. So let's move forward to the next question. This is from Marie Joanne. She asks, in your hysteretic curve, did you use the displacement data from the actuator or from the sensors?
Okay, in these protocols, we use several sensors, but we compare the curve. If I calculate the moment rotation curve with the sensor of the hydraulic actuator and with the sensor that is outside of the hydraulic actuator, and we have a similar curve, but in the reports we are using the sensor that are outside of the hydraulic actuator. Yes.
Okay, great. We have here a comment of Javier Mora, but this is more like he say many new perspectives on building with bamboo, great work. So it's like a congratulations to you. There's another question from Pap Suarez, but I think that we already answered in my question about the cost. This person was asking about comparison with other systems. I think we already addressed that question. And we have here the last question for Carlos Patiño that say, Jonathan, how do you think that the viscoelastic long-term relations can affect the joint's performance? So how do you think basically the creep is going to affect this in the long term?
Yes, I think the creep it's a phenomenon that always are present in this kind of connection because bamboo is a natural material. We have found that when we apply a high radial compression on the slats, the creep can decrease significantly. So that was from some pilot tests, but I think it's necessary to explore what happened in overall joints or in overall frames or structures with this phenomenon. Yeah.
Thank you, Jonathan. So I see a hand raised by Chris. Are we open the questions also to the public, or is going to be through the chat only?
One is okay, and then we can move on.
Yeah, okay. So hello, Chris. How are you? Nice to see you again.
Good morning, you as well, Luis, and good morning, Jonathan. Buenos dias. I'm sorry if I was out of order by raising the hand. I didn't realize it was only for the chat, but I was curious about something that came up in your talk and also in JJ's talk last week about index ratio. Number one, I want to know, can you get the same index ratio measured in direct flexure instead of using buckling test? And number two, I would suppose that even if you just had a natural comb, there would be an index ratio not equal to 1 because of imperfection. So I'm just trying to figure out what would be, let's say, a baseline expectation of index ratio from a whole comb, and again, why it's done only in buckling and not maybe in flexure, if that might be easier to do that test.
Okay, the first question was about what happened with the index ratio where the elements are support flexural.
Yeah, in other words, could you calculate the index ratio using a flexural test instead of a buckling test?
If you do bending instead of compression with buckling, so do you think you're going to get the same results?
I think in the flexural condition, this depends on the direction that we are applying the load. For example, I think if we apply the load in the circumferential direction of the slats, that is in the perpendicular direction of the pins, I think the index ratio can be high because the connections are not working a lot in this direction. So the index ratio can be good or near to the optimal. But if we rotate the specimens 90 degree, so the participation of the connection can be affect significantly the index ratio. So in this direction, I think depending of the kind of connector that we are using, I think if we are using bamboo pins or balls without a preload, so we will have low index ratios. But if we use plain slats with a high tightened balls, maybe the index ratio can increase.
Thank you, Jonathan, for the explanation. Okay, so I think we need to move now to the next presentation. I want to say thank you to Jonathan for this presentation, and thank you for everyone who made questions. I think what Jonathan's just showed us is that the bamboo possibilities out there are infinite. We just need to be creative with the way we think this material for the future. And I think his work is showing us new possibilities for bamboo that will bring us to, I hope, a good field in the future. So thank you, Jonathan, again. Continue with the great work that you are doing. We are very proud of you. Here at BASE, you are one of our students that came to work with us. So we hope to see you again here in the Philippines or in Colombia. Thank you, Jonathan. So let's move now to our next talk. In this case, we're going to have the presentation of Mes Favel. So Mes Favel is a student from the Eindhoven University of Technology in the Netherlands. Mes Favel is doing his master in civil engineering, and we had Mes for 6 months working with us in the laboratory of the Base Innovation Center in Manila. During his time, he was working very hard to make a test in CBFT, composite bamboo shear walls, and he was or bareque encementado, as we call in the Latin American world. And he's now completing his thesis and writing a paper and preparing all many information. So it's a pleasure to see you, Mes. Welcome to the conference, and I hope you share with us very interesting information. His presentation title is Analysis and Characterization of Composite Bamboo Shear Walls. So how are you, Mes? Nice to see you.
Yeah, nice to see you as well, Luis. It's been a long time. First of all, thank you for the opportunity to share the work that we've been doing. Yeah, thank you also, Jonathan, for the nice presentation. I will go and share my presentation. Let's see. All right. So I think we go here. All right. Is it visible?
Yeah, but not just there. Okay, now it's perfect. So
All
please go
right.
ahead.
Great. So, good evening, everyone in the Philippines, and good day to the rest of the world, I guess. I'm going to share the work that I've been doing at Base Baha'i, which focuses on the composite bamboo shear walls, which are also included in the new book. So, yeah, great to see. First, I'll tell you something about Base. So Base Baha'i is a company that researches the use of bamboo structures, and one of their main systems that they apply in the housing is composite bamboo shear walls. So they apply it in some projects in the Philippines, but also Nepal, India, and Sri Lanka. In the Philippines, they're using a local species. It's called Bambusa blumeyana or Kawayan tinik in Tagalog. So the nice thing about this type of structure is that it has a good ductility ratio. So it's a very good for use in seismic areas. About the work that we've been doing at Manila, Base Baha'i has a innovation center where they do some research, just like Jonathan did on the Pinbu connections, or the Pinbu columns. And yeah, there's a space for all kinds of testing. So together with Joanne, I have been working for 6 months there on the characterization of composite bamboo shear walls. So yeah, what we did is test full-scale bamboo shear walls. And then my personal goal out of this research, what I'm also working on with my graduation, is prediction of the composite bamboo shear wall behavior by modeling it, which is what I will also present in this presentation. So let's dive into it. Let's see. First, I will explain a little bit what is the layout of a composite bamboo shear wall. As you can see, it's consisting of a frame and a cladding, and the frame and the cladding are connected by fasteners. So those three elements are basically what make up the shear wall. And then inside of these elements are individual components. So As you can see here in the figure, our scope of our research is a standardized shear wall of 2.4 meters in height and in width, and using 5 bamboo studs, a top and bottom timber plate, and what we did is we tested 2 different configurations. So one with a flat bar bracing, which you can also see in the figure, and we also tested one without the flat bar bracing installed. What's good to mention is that you can also use, in our testing, we used a steel mesh called riplath, which is used to plaster the cement mortar, which makes up the cladding. And you can also use esterilla or tatat in Philippines instead of the steel mesh. But for our research, we left it out of scope. So we just focus on the riplath. What you can also see is that there is a bunch of different connections used in this frame, and I will go through all of them in the next slide. So first of all, the bamboo studs are connected to the timber plates, and that's done simply by some common wood nails. There are 2.5-inch nails that are used, and a total of 4 nails are used to connect one side of the bamboo to the top and bottom timber plates. Also important to mention from this graphics that we use, you can see that we try to select the bamboo studs used in the frame based on their length. So the internode length, we have to make sure that the ends of the bamboo studs are a node so that you have more resistance against splitting. Otherwise, you will not have a proper connection between the bamboo studs and the timber plate. Then for the installing of the flat bar, we use a bolt, and it is connected to the timber plate at all the corners, and it's connected to the intermediate and the center bamboo stud. Then for external connections, we have embedded rebar, which can be seen in figure 3 here. It's installed in the edge studs and also in the center stud. And this provides a connection of the bamboo frame with the foundation. And then to connect the frame with the roof, there's also a J anchor or J bolt installed, which you can see in figure 2. And both of these connections are then filled in with mortar to provide extra strength and extra resistance. Then the connection between the frame and the cladding, it's done by nails. So you can see that on the right. There is nails that connect the frame to the timber, and also nails that connect the frame to the bamboo. And then together, this makes the connection. Now, an important thing to mention here is that we assume the flat bar to be embedded inside the cladding. And this is because it's all tied into it, and the mortar plaster, when applied to the riplath, also encapsulates the flat bar. All right, then for the connections, this is a bit of an overview for the nailed connections, which are a big aspect of this wall system. So what you can see here is a section of one bamboo stud, and you can see that for the connection with the cladding, the nails are actually placed through the wall of the bamboo comb. And then because of that, you get a different interaction for places where mortar infill is applied or where there is no mortar infill applied. And this is a very important point for the capacity of the total shear wall, which we will get to in a bit. Also, you can see here again that for a proper connection, we use bamboo that has nodes very close to the edge. All right, then if we consider all the fasteners, so the nails and the bolts, when bracing is applied, then we can schematically lay them out like this, so that you get an overview of what type of embedment or what type of connection you have in which position on the frame. So I will just quickly go back to this slide. So for the figure that I just showed you, the frame is actually the same shape as the layout, and that's because the fasteners are positioned along this frame. So what's interesting to see here is that there's mortar infill applied at the edge studs at the top and at the bottom, and you have some bolts which are along the flat bar bracing. So then with these fastener types, we have a good, we have a very good representation of our frame, of our connections. And then we can use this to, for example, model the shear wall. But first, I want to show you the testing that we did. So here is an overview of all the testing that we did. We wanted to be able to make a prediction of how the shear wall behaves under loading. And for that, it's necessary to look at the single connections used in the shear wall. So we did some partial testing. So we did single fastener tests. And then after that, we also did some full shear wall testing. Then for the equipment, we used a UTM, which is available at the Base Innovation Center. And for the full shear wall testing, we used actually the same test setup as Jonathan, only applied it at a different height. All right, then for the single nail testing, this is what the test setup looks like. We tested only the bamboo connections because for the timber connections, we assume to be able to use the Eurocode since it's already quite well documented. Then what you can see here is that it's just monotonic testing of the two connection types, which are a nail applied in hollow bamboo or a nail applied in mortar infilled bamboo. And on the right side, you can see the expected behavior. So for the hollow bamboo, we assume that the embedment strength of the bamboo is actually governing for failure of the nails. And in the mortar infilled bamboo, we assume that it's being clamped, and then because of that, you will get yielding of the nail before yielding of the mortar. So then it's a different failure mechanic. Then from the testing that we did, we actually also found this kind of results. Here are some pictures. So in the left picture, you can see failure of the bamboo, failure of the embedment. So it's yielding. Then in the second picture, it's not that clear, but if you look closely, there's a very curvy nail. And this is because it's mortar infilled bamboo, so it's yielding of the nail. And actually something that happened in all of the testing, after a certain displacement, then it's also the riplet which loses its capacity. And basically the riplet just ruptures, and then there's a total separation between the cladding and the frame. Well, these failure modes are very interesting to take with us to the actual full-scale testing. And yeah, here's the same conclusions listed again. So with this knowledge, we can move on to the full-scale testing. Here is the test setup that we used for full-scale testing. So we wanted to do both monotonic and cyclic testing because we also want to see what is the seismic behavior of a composite bamboo shear wall. So yeah, we wanted to purely test it for shear capacity. So what you can see is that there's tie-down rods applied. They are indicated in blue here in the figure. And these tie-down rods, they assure that there's no overturning of the shear wall. So the only failure mechanism that can occur is the shear failure. And then that's where the single fasteners come in because shear failure is then only caused by the connection between the frame and the cladding, which is the fasteners. Here is an overview of the testing protocols that we used. These are from ISO 21581. For monotonic testing, it's basically proof loading and then releasing that proof load and then testing until failure. And then we actually used the data from the monotonic test. So we used the failure displacement to cater the cyclic testing. So for cyclic testing, it's basically you increase the displacement. So you control the displacement and you increase it until this failure displacement retrieved from monotonic testing. So yeah, with this, we started testing. I wanted to share with you some of the videos that we have. So first of all, I'll show a monotonic test, and then after that, I will show the cyclic test. And for the cyclic test, we did them at a very high pace, so it's also very nice to hear the sounds that come along with it. So I hope you can hear it from the presentation. First, here's the monotonic test. So what's interesting to see is that if you look closely at the cladding, it is actually rotating a little bit, and I'll show it again. Oh, wait a second. I'll show it again just to show you. So what you can see is that at the top left edge, there's actually a small gap between the cladding and the frame. And at the top right edge, it's actually gone over the frame. So this is interesting to see. It's actually one of the things that we can also use for the modeling of the shear wall. So I will get to that in a little bit. Now, if we take a look at the cyclic loading, and I have filmed this from the other side, so you will get a different view. It's also interesting to see what's happening to the frame. So here you can see it. And you can also definitely hear all the creaking noises. So it's really the bamboo that's working. Now, what's interesting here is that, again, you can really see that the cladding, it's rotating. So instead of having the mortar or the cladding itself to resist all the loads, it's actually just acting as one solid plate element. And the failure of the shear wall, it's actually only caused by the fasteners. And then it's interesting to see that in the corners, you will have the most displacement. Now, this brings us to the point of the bracing. We wanted to test the shear wall not only with the flat bar bracing applied, but also without. And then it's interesting to see the difference because, well, initially my thought was that the bracing would actually provide a lot of the shear capacity. But it turns out it's actually not so much necessary for shear capacity. It's more necessary for example, out of plane effects. So in the next video that I'll show, you will see a shear wall without the flat bar bracing applied. And then what you can see is separation between the frame and the cladding. So this is actually the cyclic test, and it's already quite far in the testing procedure. So what we notice is that after maybe 7 cycles, we already reached the maximum load. And then for the last couple of cycles from our cyclic testing, that's really where you start to see damage. So this is one of the last cycles that we tested, and you can really tell, especially if you look on the far right, there's total separation between the frame and the cladding. So yeah, it's really interesting to see what kind of unexpected effects some of the elements used in the composite bamboo shear wall have. So let's move on to some failure modes. So most obvious one is, of course, the yielding of the fasteners, so the yielding of the nails. Also one that is caused by the corners being pushed into the testing frame. It's crushing of mortar. Then separation of frame and cladding. That one we mostly saw for the test that we did without flat bar bracing. And where we did apply the flat bar, you could also see some buckling of the flat bar when it's loaded in compression. So with that in mind, I would like to move on to the theoretical part. So what I wanted to do is make a model that can be used to predict the shear wall behavior. And actually the goal of this is to accurately describe the behavior of composite bamboo shear wall. And then, for example, it can be used to optimize the structure or to find some better alternatives for certain types of fasteners used. So this part, it's quite theoretical, so maybe I will just briefly explain it. This is actually the way that it's set up. So as you could see from the videos, when a displacement or when a force is introduced to the composite bamboo shear wall, 2 things will happen. One is that the frame, it will start to deform horizontally and only horizontally. And the cladding, it will start to rotate around its center of gravity, which is also the center of the frame. So that yields the movement that you can see on the right side of this graphic. And what's interesting about this is that you can actually use this to calculate all the distances between the frame and the cladding in each position. And this is actually what we use because all the nails that are in the composite bamboo shear wall all have a determined position, which is also what I showed in the graphic before, the schematic overview of all the fasteners used. So when you know their position and when you know the rotation angle caused by the horizontal force or caused by the displacement, then you can calculate what is the displacement of each individual nil. And this is actually what you can use to kind of calculate or predict the capacity of the shear wall. So here on the right side, you can see in both the horizontal and in the vertical direction, kind of a calculation method to predict or to predict what is the force exerted by each fastener in the system. And it's decomposed into X and Y direction, because then, for example, you could also implement whether you would include some of the intermediate studs in the horizontal direction, for example. Because from some of the videos, you could also see that maybe the connection between the intermediate studs and the timber plates on the top and the bottom, it's actually not that good. So then, for example, you could implement in the model that there's only vertical components in those fasteners located on those studs. So yeah, using this information, we can kind of derive some relations. So this is actually something that I'll skip for now. This is derived from a very interesting paper written by Gausner and Gearhammer. They applied the same theory to timber framing. But what's important from their theory is that you can define a formula for the rotation angles. So, which I showed here, you have a angle gamma of the frame, and you have an angle phi of the cladding. And those angles are actually related to the stiffness of all these fasteners used in the shear wall. So this is the relation that you have, and actually the basis of the relation, it's the distance from each single fastener to the center of the shear wall, and it's that distance in the X direction and in the Y direction separately. So if you know that, if you know what is the distance, and you know what is the stiffness of each of the single fasteners in your shear wall, then you can already define your angle gamma or your angle phi. And using this knowledge, you can actually also you can also find the capacity or the stiffness of the shear wall. So this is actually really interesting, and this is something that I have now used to make a model. So yeah, this derivation, I'll also skip it for now. I just wanted to share with you what's the theory behind it, and then what you can use it for actually. So when you know the stiffness of the entire shear wall, you can just integrate that to over the displacement of the entire shear wall to find a force. And that force, that's actually the horizontal capacity that you then have. So it's actually really interesting to see that you can use the knowledge of each individual's fastener to derive a total horizontal capacity. Then here is a relationship of all the force displacement diagrams that I used for each individual fastener. And I used these actually to already develop a model. And I just wanted to share what the force vectors in this model will look like. So here is an overview of the forces as they develop with an increasing displacement of the total shear wall. So on the top of the figure, you can see a U value and the U value is increasing, that's actually the displacement of the total shear wall. And then what you can see is that as the shear wall displaces, your fasteners all will have a different force that they exert to to resist the horizontal deflection. So yeah, it's really interesting to see that you have a very different influence from each fastener. And you can also use this figure to kind of select where you would like to improve or change the structure. So that actually also brings us to the conclusion a bit, because now we have actually something that we can use to determine like where could we change some of the geometry, or where can we change some of the fastener types used to improve the capacity of the system. So yeah, that's what I wanted to share with you today. Let's see. Yeah, another thing that I still want to improve in the model is to also see what's the response for cyclic loading. And then I want to still apply some of this knowledge to also find a real optimization shape or fastener type to use in the composite bamboo shear wall. Yeah, that's about what I wanted to share. It's been an honor to be for 6 months at Base Baha'i to be able to contribute to this research. And also, it's been an honor to share it with you here today. So I think that's about it from me.
Thank you very much, Mes. Really nice to see your work already in progress. I think it's not yet finished. You're still dealing with your thesis. But it was for us also a pleasure to have you in the lab. We have a very interesting time working together, sharing ideas. I remember our conversations in the lab, trying to figure out the resistance of the panels, where are they going to fail. And we have this, I will not say game, but it's like trying to guess the resistance. So we always try to find who is going to be the nearest, and it was quite fun. And but aside of the nice experience in the laboratory, I will say that the work you are doing is really interesting and is an important part of the development of this technology. I think 25 years ago, when the Colombian Seismic Association did the first test and a big number of samples in Colombia for the building code, that was a good achievement, but a lot of questions were there in the air that is still not answered yet. And then I think with this work, you are trying to answer many of those questions and go to the next step, that is the analytical models and the prediction of the behavior of these panels. And this will bring us to a more interesting place. So congratulations for the work. It's so good. And now I want to see if we have a question here. Okay, then there's a here for Javier Mora. He say, thank you for your insights. Have you compared your results with a traditional wood framing wall and a light gauge steel frame construction methods regarding resistance and cost? Have you done that?
Yeah, that's a good question. Well, I think one major difference, for example, for wood framing is that in bamboo we use the cement mortar. Actually, I think maybe Nishal will mention something about that as well, but there are also some ideas to test also a gypsum board instead of cement mortar cladding. And I think that once you will use a system like that, then it becomes more interesting to compare it to wood framing actually. I think for this system, it's actually quite it has quite a good horizontal capacity, but comparing it with other materials, maybe it shouldn't be so much about the capacity, because I think with steel or even with wood, you can get higher capacity, but it will maybe be more impactful to build it, for example, in a location where bamboo is more abundant. So I think that's more the question that should be asked in this case.
Yeah, thank you for that. And then moving forward to the question of Angela Milagros, she asks you, thank you for the detailed explanation. I'd like to ask if you had any problems with natural bamboo compared to treated bamboo. That you can answer it. Answer for you.
Yeah, it's a good question as well. I think what's nice about the knowledge that's available at Base Baha'i is that actually the treatment of bamboo is one of the first steps in the process. So if you would use natural bamboo, you're much more prone to get fungus attacks or insect attacks, and then it's a lot more probable that you will get some kind of structural capacity deterioration because of your structure is being eaten by bugs. So at base we just use the treated bamboo, since then you will also have a lot more confidence in your structure staying there for a long time, and having more lifespan, I would say.
Okay, so thank you for the answer. Here we have another question from Masi, and he say, have you compared the shear capacity of the rendered grip lat wall against a rendered bamboo strip lat wall?
That's another very good question. Actually, we have done some testing with the bamboo strip walls, although we still have to continue our research on that, I would say. Because for now, I think the test specimens that we used were inaccurately constructed or fabricated, and because of that, the comparison is quite, it's not a very accurate comparison, I would say.
Okay, so here we have a very good question from Professor Kent Harris, and he asks you, in your slide 26, you show an excellent animation of forces vectors. Such a demonstration is quite useful to illustrate to engineers what is necessary. What I found odd was that the model appeared to be symmetric about both diagonals. However, a wall is a cantilever and the bracing will not be behave in a symmetric manner. I am middle concerned that the boundary constraints may require some attention in this regard. So do you have any answer about that?
Yes, I do. It's a very good question. Thank you. So that's actually one of the main reasons for doing these tests. So as I mentioned in the presentation, is for the experiments we applied some vertical restraints so that we leave out the effects of overturning of the wall. So then actually the only thing that will happen is that your wall will only show horizontal deflections. And if you look at that in the sense of the shear wall, or in the sense of this system that we use, then you can see that it's pure shear. So in that sense, when you look at the visualization that I showed you, I don't know if I can share it again. Let's see.
Just when you're looking for your presentation, I want to clarify that what Mes is mentioning is he used the method 1 in the ISO standard that have a restriction to overturning in the panel, so the panel is totally fixed to the ground, and the restriction to overturning. So you in theory, you are applying a pure shear.
Yeah, so that's also what I was trying to say. And then because of that, you just focus on the effects of pure shear. And then actually, in that sense, the symmetry is very easily explainable because if you have pure shear, then you will get so diagonal pulling in one direction and diagonal pushing in the other direction. So that's actually a very good thing to see in that case.
Yeah. So thank you. I think Edwin, you were raising your hand. So
Yeah, just briefly, very interesting presentation, Miss, and thank you for joining us today. I was very impressed by the sound. We often discuss how energy is dissipated in these systems, and even at these low frequencies, you could hear very well in your videos. I hope I can get a copy of you. I don't know if you're taking that in account in your calculation.
Yeah, that's a good question. So the capacity of the nails, it's actually dependent on the embedment strength also of the bamboo. So the cracking, what you hear, it can be a lot of things because you also have, of course, some horizontal movement, but I believe that most of it is caused actually by the bamboo splitting, and then that happens where you apply the nails. So you will, as the deformations increase, you will get more embedment failure, and then you will get some splitting occurring in the bamboo. And I think this is actually also the reason why this structure is so ductile when it comes to seismic behavior, because a lot of energy is actually dissipated into this splitting.
Mhm.
yeah. In addition, I think there's a lot of friction between the nails and the bamboos. So during the movement, that friction generates a lot of dissipation of energy. But okay, we need to work on that. So I think the time is over. I want to say thank you to Mes for his wonderful presentation and his work. We are super excited to see the results of written in a paper that we need to finish, I hope, this year. Uh, and then I hope to see you again in Manila one of these days. So please come to visit us.
Yeah, I definitely will. Thank you, Luis.
Okay. Okay. Now let's move to our third presenter of the day. Let's welcome Dr. Nishal Pradhan. He is right now the director of the Base Innovation Center and Base Baha'i Foundation. He's a doctor of the Hong Kong University of Science and Technology, where he made his research about bamboo connections. He is right now coordinating all the research topics in the laboratory. He was working very closely with Mes and with Jonathan as well. So and now coordinating all the students and the research and about bamboo in the laboratory. So his presentation is called Engineering Resilience Towards the Rational Design of Bamboo Structures. So let's please welcome Nishal.
Yep. Luis, thank you very much. Can you see my screen? Let me try this. Okay. How about now?
Yeah. Perfect.
Okay. Great.
Nishal.
Yeah. So Luis, thank you very much. So I'm going to talk a little bit about what Base Baha'i does and what we do in our laboratory that we call a Space Innovation Center. And as you can see in the previous presentations, both Jonathan and Mace worked in our laboratory. So in the next couple of slides, I will explain a little bit more detail as to what kind of research opportunities are available, so that if you guys are also interested in working with bamboo and you want to work with us, please feel free to send me an email, and then we can discuss. I can also provide some stipend. I can provide some accommodation to support your work. So first of all, Base Baha'i Foundation was established to provide alternative building technology to enable affordable, dignified living to people in the Philippines. Now we are expanding gradually throughout South Asia, but originally it was primarily for the Philippines. And we operate through three different arms. The first one we call as Base Innovates, where we lead research and development of bamboo-based technologies. The second arm, which we call as Base Builds, is where we work with architects, structural engineers, construction workers, to transfer the technical know-how and also to enable you guys to build with bamboo. And the third one, which we call as Base Enables, deals with training and value chain, where we work with treatment centers, bamboo harvesters, so that you guys can get the high quality bamboo poles that you would need for building bamboo structures. So our core technology, we call it as cement bamboo frame technology, has quite a few interesting features. And they are like, they have very good, they are a permanent housing solution. So they have a minimum lifespan of 50 years. They are engineered structures, as in they are designed to resist typhoons and earthquakes as per local building codes. And since we use only chemically treated bamboo, they have insect resistance and fungal resistance. Certain specification of wall have fire rating of up to 120 minutes. And if you compare this technology with our closest, alternative, competitor in the market, we are generally 20 to 30% lower for the same floor area. These are some of the houses that we built over the years. You can see single-story duplex houses. You can see two-story houses. We can even build, houses that are designed to respect culture of the Philippines. We have two-story single-detached houses as well. And you can see this is a middle-class house that one of our partners built. And, he has set up a treatment facility called as Kawain Collective, and you can actually work with him and also buy bamboo houses like this from him. This is how the houses look from the inside. You can see all the bamboo structural systems that's clearly visible. And we proudly show bamboo from the inside, there's nothing to hide over here. But there are certain cases, for example, in bathrooms, kitchens, where we don't want the bamboo to be exposed. So we have cladding over there so you don't see bamboo, right? And if you're working with the two-story structures, we do have like bamboo-based staircases as well that you can see over here. And, this is how all of our houses look like in the field. You can even use the technologies to build, other non-residential structures. For example, community centers, school buildings, office buildings, even industrial buildings such as weaving centers and food processing centers. Now, you have to realize that when you work with bamboo, unlike conventional materials, that you don't have any knowledge base to work with, which means we have to create our own knowledge to support our work. And as a result, we have established a laboratory here in Philippines, which we call as Base Innovation Center. And here we do fundamental research, applied research to develop all the technical know-how to design and build our structures. So all the results of our research and development, we use it to also write building codes and standards. Actually, we've written building codes for Philippines, updated building codes for Colombia and Nepal. And next year, we're going to work with Fiji and Peru to help them develop their building codes as well. And, the same technical know-how, we also transfer to training and learning so that we can transfer this knowledge to you guys, and you can also use it to design your own bamboo structures. And now, in recent couple of years, we've started exporting this technical know-how to our, partners across Asia, for example, in Nepal, India, Sri Lanka, Bangladesh. And, I want to talk a little bit about the impact of all of our students that have joined. So up to today, we've had about 300 plus local and international interns who have worked on over 91 student research theses. And collectively, we published 12 journals and conference papers. So you can see beyond this, the types of documents that we have developed. This includes Philippine guidelines, the first ever textbook on structural design, Colombian structural code, guidelines for Nepal that was just approved a couple of days back, and also a construction manual that you can use like a cookbook to build your own CBFT house. At the same time, we're also working with ISO, RILEM to develop international standards. And I'm proud to say that Base Baha'i Foundations have 3 international experts representing Nepal, Colombia, and also Philippines in the ISO standards for developing bamboo standards. We have had students from all over the world. This year, we've had over 100 students, 1 student approximately from each continent. And you can see, students from ETS Zurich, Hong Kong, Switzerland, Virginia Tech, Coventry University. Even, we've had interns from Nepal. We have interns from, Indonesia, Japan, so there are so many people coming from all over the world to work with us in our laboratory. So that's why, the lab is open for you guys. If you want to work on something related to bamboo, please send me an email and we will find a nice topic that you can work on and make a real impact to the construction sector right now. So within Base Innovation Center, we are primarily focused on 3 different types of research. We are working on mechanical properties. We are working on performance of connections, and then we are trying to understand the behavior of structural systems. And you saw in the presentation of Mace how we are trying to understand the behavior of cement bamboo frame technology walls. So our primary goal here is to develop to contribute experimental data needed for engineering design and ensure safe and reliability of bamboo structures and to feed the development of codes and standards throughout the world. Now I will start moving towards the the topic I would like to talk a little bit in more detail, and that is in terms of mechanical characterization. Now, if you think about this, globally, you have over 1,600 bamboo species available. Out of 1,600 bamboo species that are available, maybe about 100 species are used for structural use, and out of those 100 species, less than 20% of these, less than 20 of these species are characterized. And out of 20, Base has been working to characterize about 7 of these species. And, you can see some of the species that we are nearing completion. You can see Bambusa blumiana, Dendrocalamus asper, Guadua, Bambusa vulgaris, and Bambusa meridiana. So out of these species, Dendrocalamus asper, Guadua, and Bambusa vulgaris, we consider them as global species. So if you're working in any part of the world and you would want to get some data on these species, please let me know. I can share this data with you so that you can do structural design and work with and build structures out of these species. Now, in terms of characterization, you have to realize that in order to do a full, complete characterization of a mechanical characterization of a species, you need to do 6 different types of tests as specified in ISO 22157. This includes compression parallel, shear parallel, tension perpendicular, bending perpendicular, and bending parallel. So these are like 6 different kind of rudimentary tests. And you need to do about 30 tests. Actually, ISO says that you need to do 30 tests minimum. But when we started doing these tests in our lab, we realized very quickly that 30 tests is not enough. The coefficient of variation, or the natural variability of bamboo in the form of round pole, is so large that the 30 test is not enough to capture the full variability. So that's why what we did is we are now doing 100 samples minimum for each species of this. So in order to fully characterize one species, we are doing about 800 tests. So compression, 100 for compression, shear. For tension, we have to do 300, and then we took and from the 300 we have to take the minimum 100, and so on. So for tension, bending, and bending parallel, we take 100 each. So we have to do at least 800 tests in order to fully characterize the mechanical properties of the species. So here's an example, of bending, strength parallel to fibers. You can see how the distribution is observed, and you can see that the strength varies between 40 to 140 megapascals. And whenever we are doing for design, we never design with average. Actually, we have to look for a lower bound, and what we call this as a 5th percentile value. And you can see that it's about 57.03 for this data. And this is a sample value, and we need to convert that to estimate the 5th percentile of the population. So through mathematical acrobatics, we can figure out that we call this as characteristic value. And this gives you the 5th percentile value of population. You can see it's a little bit smaller. And on top of this, you multiply with further modification factors of safety, and you get a final design value of 15 to 20 megapascals. So you can see, you know, any design value when you use, you're working with a so small value, and you can see that there is no specimen in the laboratory you will ever get a value that this small. So you have to bear in mind the amount of conservativeness that is present in this current design approach. So you have to do this for all these 6 different properties, and this is the table that you will get when you do a full characterization. So you're looking for a range of data with a range of characteristic values, and also, you know, for some properties you also work with mean. So we also produce mean values for example, for Young's modulus, for density, and so on. Now, here's the issue. Okay, if I want to characterize an entire species, I have to do 800 tests, right? And if I characterize 5 species, I have to do 8 times 5. That would be 4,000 tests. Now, you can see how crazy the numbers will go. So if I want to characterize all 100, it's going to be a super large number, you know. And if I were to do that, I would be set for the rest of my career, even my children's career and even my grandchildren's career. So what I want to do is I want to avoid doing all these kinds of tests. And I want to figure out if there is a way to, you know, cheat the system, right? So with one of our students in our laboratory, we found a promising method, and I'm going to show you how we will now do the characterization. So let's take a look and let's take an example of shear strength, right? And let's also see the geometry. So if you just compare the geometry, diameter versus thickness, you can see all these 5 different species. You don't see clear trend across species. The same with the shear strength. You know, if you compare shear strength with wall thickness, you don't see, you see some trend, but it's not really sure. For example, if you look at the Bambusa bloomiana, you have a very large scatter over here. If you look at Bambusa mariliana species, you have a smaller scatter. So does that mean that the characteristic value for bloomiana should be smaller than that of mariliana? Yeah, that's a fair question, and it's the same question that you're going to be asking every single time whenever you're looking with a new species. So we need to find a solution to this madness, and here is the solution. So what we figured out is if you use certain dimensionless relationship of the properties, for example, here we have shear capacity that is which is in its dimensionless form, and if you compare that with this with a dimensionless form of geometry, you get a very, very clear trend across species. So you can see all the 5 different species that we've ever tested falls in a very straight line. It's a linear form. And this linear line can be specified with the help of equations. For example, for the mean value, you can have this upper equation here. And for the characteristic dashed line, you have a lower bound equation over here. And you can see that the fit is very nice, about 0.9 R-square value. So you can clearly see a very clear trend across species that is that you was not able to see if you just compared shear strength with wall thickness. And this gives us a whole new avenue for doing reduced testing. So if you look at the prediction of the equation that I just showed you, you can see that the mean gives you approximately unbiased, you know, median response, like 50% response. You can see here 50% is above, 50% is lower. But at the very high capacities, you can see that the equations over predict the experimental, and this is expected. This is expected because in that particular equation, probably I did not consider the parameter that is causing failure in these specimens, right? But in general, most of the specimens that I've tested, I can see that it falls, or it gives you an unbiased response where you have 50% over prediction, 50% lower prediction, and there is a clear trend in you know, predicted versus actual force. And you can see even the characteristic value. When I plot this characteristic curve, only 8% of data points fall below this line, which means it is very good for. It is a very good equation that you could possibly use to design for shear. Now, We tried this with a completely new different species that was never ever used to calibrate to this line. And you can see that new species, here you can see Bambusa balcoa and Bambusa nutans, which we got from my colleagues in Nepal. So it fits very well in the same plots, meaning the equations that I used to calibrate using the 5 Philippine species that I tested in my base innovation center, I could potentially easily use it to predict the shear capacity of Bambusa balcoa and Bambusa nutans very easily. So that's the idea, And, so I'll give you an example how to do it. So for example, for Bambusa balcoa, all I need to know is its density, the mean density, which is 720 kilograms per meter cube. So I assume a thickness value 10 millimeters. I assume a diameter value 80. I calculate the x-axis minus 2.8, and then I fit into the characteristic equation. I will get a value shear capacity of 16.43 kilonewton. Now this value is a value that you would get as if you tested a real specimen. So I need to use the ISO equation to convert to a shear strength formula, which I do over here, and I get a characteristic shear strength of 5.13 megapascal. So if you look at, characteristic value of shear strength for other species, you will find that it fits that data range very easily. Okay, so if you think this is a coincidence, I will give you another example, and another example with a species from Sri Lanka. My colleagues in Sri Lanka was very eager to very graciously send me those data, and I can see this data for compression, and you can see how even the equations that are calibrated for compression works really well for an unknown species that was never used to calibrate to this equation. So you can see Dendrocalamus sucuri with the density of 750 kilograms per meter cube. I assume a thickness of 7 and diameter of 70. I put in the x-axis values. I plug in the equation for compression and I get a compressive capacity of 51.94 kilonewtons. Now I convert that to strength and I get a characteristic compressive strength of 37.49 megapascals. So you can see when you're working with an unknown specimen, all you need to do is you need to find out where your species lie on the x-axis, and then you choose a pertinent value in the x-axis, and then you can use this dashed line to find the corresponding value of y-axis. And once you solve the equation, you will end up with a characteristic value of compressive strength that you can easily work with existing bamboo codes and standards to do your design for shear, compression, and similarly for all the other mechanical properties that you will need. So you don't need to test 800 samples anymore. You can just probably test maybe 5 to 10 samples per species just to verify where that species fall in this line. And you just use this equation to do your design from there onwards. So thank you very much for listening to me. If you'd like to get involved with us, just let me know, and I'm always there to collaborate with you guys. Thanks a lot.
Thank you, Nitzschal, for this presentation, also for sharing the information about BASE and what we are doing. I think this new methodology that we are still testing for each of the properties is very promising, and it will help us to create a protocol that support the development of the construction industry with bamboo. I mean, one of the limitations we have is that we don't know the properties of many species, and in continents like Africa, for example, there is not too much information because also there is a lack of laboratories, and make these tests is expensive, by the way. So we hope that with tools like this, that probably in the future we can develop like an app of something more sophisticated that people in those places can use, and then just with a very small number of tests, and they load the information, they can get good and safe, more important than everything, safe values for this. So this is a wonderful work that is being done by a group of students. Maybe you can mention them and say thank you to them, because this is the work of many people in the Base Innovation Center.
Yeah. So this research was led by Anjanette Gonzalez. She's a master's student from Mapuya University, and to support her research, we have an army of students from De La Salle University, University of Santo Tomas, also Maputo University, who have like who has been sending like hundreds of students every year to help us do this test. So it's a very interesting. I mean, we are honored to receive such high number of students and such quality of students in our laboratory, and I'm really grateful for them to join and help us explore these ideas.
Okay. So let's go now with the questions. So we have here a question from Tobia. He's asking, is there a chance to connect Indonesia as well with your project?
Yes. So we've been thinking of working in Indonesia, and I mean, and everybody already knows Indonesia is a very high area with very large bamboo constructions happening. And yes, we want to work with people like you. If you're in Indonesia, please let me know, and we will connect and do research together.
Right now, Base Baha'i has a partner in Indonesia, it's Bamboo U. We are working with them on the topic of training more. And we're also exploring new collaborations there. So I will move now to the next question from Professor Ken Harris. I think he has two questions. So the first one is, using a dimensionless approach is excellent and appropriate. Nonetheless, confirmation by others is critical. My concern is that all this data is produced from one laboratory. We need to assess potential for systematic issues and inter-laboratory variations and bias.
So Kent, I knew you would ask that question. That's why I had these slides at the end. Let me see if we can find that again. So here, if you look carefully, you can see how the equations that we developed for BIC works well for samples that was never tested in BIC. So this samples, Bamboo Sabalco and Newtons, was tested entirely in Nepal in a different laboratory, different system, different climate, different region altogether. And you can see it works really well. And then if you think Nepal is, because I live in Nepal, maybe I had some contribution, you can see data from Sri Lanka over here. So this is Dendrocalamus suckeri. Now this was completely independent, complete independent number of people, different researchers, different environment, different species altogether, and you can see it still works very well with this species. So we can continue doing this again and again, but I think the answer will be the same. If you can see, if I answer your question.
I think, Michelle, I think that's excellent, and I'm not questioning your data. I'm kind of making a point to the community here. Because you do have data from different sources, I think we can start establishing interlaboratory bias data. And this is critical because you have that's also part of establishing a good, solid standard, is understanding what that will be.
So let me interrupt and answer that. I totally agree with you, Kent. We are just completing the information about this process because we think it's an interesting approach, and it should be out there so more people can start to test it. And definitely we are totally open and preparing. Once the paper is released, immediately, and this is already agreed between Michelle and myself, that we are going to open all the data for the RILEM group and for the construction task force also, so everyone can work with our data. So we are just waiting to this paper. Nishal, when the paper is going to be ready?
So I think we are at 80% to 90% completed, and I hope maybe we can submit early next year, hopefully January. So
I do have a proposed journal for you too, if I put my other hats on. I think it's excellent work.
Thank you.
We'll see what we can do.
So let's see, I think another question here from Javier Mora. We have in Ecuador to a factory processing bamboo. We would like to be in contact and share technologies. I think, Nishal, you want to share? Answer, sorry.
Of course, yes. The default answer from us is yes. And actually, we've been working with treatment centers, bamboo processing factories, not just in Philippines, but also in Sri Lanka, Nepal, and so those two countries, so and how we do it is, we usually have remote communications, and sometimes our Filipino our Filipino engineers will come to your facility to do an inspection, and then we help you establish a very well and coordinated treatment facility. So the answer is yes, and let's connect and see how we can work together.
Perfect. So Edwin, do you want to say something before we
Thank
start
you.
the session?
Just very short. Nishal, thank you very much for the presentation. I was wondering if these equations that you're using would also apply for the small diameter bamboos, like the ones we find especially in Africa. Or
that's a
just
good question.
can we think on a similar approach for the small diameter bamboos? Because I think there's where we have almost no information on mechanical characterization.
Okay, that's a very good question. Let me go back again. If you look at the plot over here, that's why we are working with T by D ratio, So even if the diameter is small, the thickness should also be proportionately small. So chances are that it will likely be within this range, So when we start putting in the data from African species, I feel that the data will fall within this range, and I hope that the equations can be used. We do have a small diameter species in our laboratory in BIC at the moment, and we are planning on doing some mechanical tests. So it would be very interesting to see if it works on small diameter as well.
Just to add, I think very, very interesting question, Edwin, but the Dendrocalamus hookeri that you see in this slide is a small species. Actually, the size is very similar to the African species. So okay. I'm sure it's going to work. Okay, so...
Can I comment on that just for a second, Luis?
Yes, sure.
I think one of the things we do need to be a little bit concerned with the small diameter is some of the test methods, not all of them, are probably not appropriate for a smaller diameter. And so let's be a little bit careful with extending this beyond, let's say, below 40 millimeters, because some of the test methods are probably are no longer appropriate. I will state that as a fact.
Absolutely. And we are concerned also with that. So that's a topic that we need to also discuss for ISO 22157. So anyway, so just before we close, I have a question here that I think will be interesting to have maybe a short talk. It was first posed by Masi and then second by Kent, and I also agree that we should discuss for a couple of minutes about the situation in Hong Kong and the fire of the scaffoldings of these three buildings and what happens there. And the question is if this is going to affect bamboo construction, and definitely it's going to be a bad news from my opinion, and it's going to create a lot of concern about bamboo construction. But also we have to understand also that this is a scaffolding, it's not a building. Okay, it was not a building made of bamboo that was burned. It was a scaffolding that has no any fire protection and is totally flammable. So I don't know, Ken, you want to say something that you mentioned it there?
Yeah, I think this is a concern for the industry. Obviously, whenever there's a tragedy, and the one thing that it's too early to start talking about this from a structural perspective. I mean, regrettably, there are still more lives to be lost. I think that we need to recognize that what comes out in the media is not always particularly accurate. And I've seen a lot of media, very good media, The Guardian, CNN, saying, oh, bamboo, it's burning and it's caused the fire spread. Look at the images. We have a burnt out building with the bamboo structure still in place. The fuel that's provided by the bamboo is not adequate for the fire spread that we saw. There are a lot of other issues that are slowly coming out. Improper use of polystyrene as an example, that really contributed to this. I think there's going to be a little bit of dispelling the myth. Personally, I'm not remotely concerned about the use of bamboo scaffolding from fire spread perspective. There are some other issues, obviously. But I think it's important to recognize that, and not just yet, but it's important to get that sort of word out there. We're getting a bad reputation for the wrong reason.
Yeah. So anybody else wants to discuss? I think, I mean, it's hard. When I saw the images in my head, I immediately say, oh, I mean, this is going to be bad information about bamboo, and we were going to erase a lot of questions out there. But I think as professionals that believe in the material, we need to continue working and showing the capacities, and also providing solutions for fire and construction and real construction, because we cannot compare a house made of CVFT or a house made of engineered bamboo versus also a scaffolding made of bamboo. That nothing against the scaffoldings made of bamboo, actually, but they are two different things. Yes, Chris, please go ahead.
Yes, thank you. I certainly concur with what you and Kent and others have just said, but I just have a question, more of a curiosity. The article I read this morning in the New York Times said that China had already prohibited the use of bamboo scaffolding, as if this was some years ago before this tragedy. I'm just curious if that's true, and if so, what was the reason for that?
Yeah, I have no idea about that information, Chris. Okay. So I think this is a good reflection for the end of this meeting also, that we are also facing some issues that we need to work on. Fire is probably, before I used to say connections is the topic that we have researched less, and now I would say fire is probably the topic where we need to focus because there's not too many tests. I mean, there's still a lot of unknown things about fire and bamboo that we need to work. Okay, so by saying that, I conclude this. So I pass to Edwin now to close the event. And
Okay.
Thank you very much for all your attention and for staying with us the whole presentation.
Thank you. Thank you, Luis Felipe, and to all the presenters. Really is very important, especially the spirit of sharing. I need to highlight that the work you all guys are doing and sharing it with everyone is so important that we can advance. To share, we have now Durai from some closing remarks for our online seminar. So, Durai.
Thank you, Jedwin. I think my sound is clear. I wanted to. Okay, great. Hi. So I think it's great to see colleagues who has been like constantly in the construction, like some webinar, like so many thanks indeed for all of you. So I think like continuing the webinar session for the past 5 years, like some which we started with like COVID. So like we have stopped all the other like some webinar, only the construction like some webinar has been like some continuing all this time along. So that itself proves that there is a huge demand for the bamboo construction. And so the amount of like some people still participate in the webinar by itself is a proof that the quality of the presenters and the quality of the research information shared across is quite great. So in this conference, we had 4 like sessions, as all of you know. We have been analyzing the LCA aspects of the bamboo as a building material, scalable models on like some bamboo construction, along with like INBAR we have done the application of the bamboo materials and advances in the characterization. And nowadays, like Asian is focusing on engineering with like some bamboo. So there is huge scope still to do the research innovation on like some various aspect. In particular, as always Philip and Edwin have indicated, like fire is a very important area, and this has been always and very important area. So if we have to mainstream bamboo as a construction material in the government buildings in the countries like India, China, or even like so many African countries, the suitability of the biological material against like fire is a very critical element. So, we have to scale it up. So our like some further like research could focus more on the fire aspects as well, in addition to all the other elements. So this session, this conference have also enabled INBAR and like Case Baha'i Foundation to like some publish an construction manual on how to construct the bamboo construction. And along with I Structure E, we have also developed an manual for the bamboo structure. I think always Edwin and other colleagues are the key persons of this manual. So it's a great achievement, and it will be a great contribution to the bamboo sector in the future. So as I have indicated before, we wanted to extend our gratitude to like over like 1,000 like some participants who have registered from across like 60 plus countries globally. And on behalf of INBAR, I would also extend my special appreciation to the international speakers for sharing their knowledge and like research from Canada, China, Colombia, Germany, India, Indonesia, the Philippines, Switzerland, and the United Kingdom. So we have the participants across the world, and also we have like some speakers from across the globe. And in particular, I wanted to recognize the contribution of the INBAR Construction Task Force and their ILM colleagues for the session moderation and the presentation delivery. I see Edwin, I see Luis Felipe, I see like some Ent Harris and other colleagues from the construction task force who has been active in the past 5 years. Like without whose support, we couldn't able to organize these sessions of a very high quality. And finally, I wanted to thank our own colleagues for organizing team, Kuwai, Xingwai, Yuchen, like Guo, for organizing this like some webinar. And in addition, I wanted to thank our people from the INBAR communication department, having Austin, Aticia, who have like supported in promoting the event in INBAR social media platform. With that, I wanted to conclude. I wanted to thank you all again, and we hope to see in 2026. Thank you very much, and have a good day or like some good night.
Thank you, Durai. Okay, we are a bit as per usual over time. Let's make the last picture of our seminar. So please, everyone, open your cameras. And in the meanwhile, I want to thank again everyone, especially Rylem and the team of INBAR for organizing and preparing everything. Thank you to all the presenters and chairs that agreed to participate in this year's seminar. It's always a big endeavor from the task force, but I think it's very rewarding to see. Okay, let's make the picture.
Okay.
Okay.
Yeah.
Okay, thank you. Thank you very much, everyone. All the best, and I hope to see you next year in November again. Bye-bye.
Thank you.
Bye bye. See you next year.